Дмитрий Валерьевич Treschev из математического института Стеклова. Его следующий доклад, его доклад называется «Интегрированность и хаос по существованию в одной системе». Я просто не вижу иностранцев, видимо, по-русски. Здесь? I'm sorry.
Not everybody speaks Russian, so I will speak English. My talk will be on dynamics and more precisely on Hamiltonian dynamics. And usually in my Hamiltonian systems, the configuration space, the phase space will be compact, or at least energy levels will be compact. Otherwise, it is not meaningful to talk about chaos when a trajectory goes from infinity to infinity. No chaos occurs. And first, I mentioned two extreme classes of Hamiltonian systems. The first one is the most regular integrable systems. So, integrable. The phase space in this case looks like this. So all the phase space is foliated in some invariant manifold. Maybe with some singular manifold. And on each invariant manifold, these manifolds are tori, and except that very special. And on each manifold, the dynamics is quasi-periodic. So this is regular situation. And another extreme class of Hamiltonian systems is extremely chaotic. So hyperbolic. In this case, I will not give, or amorphous system, so I will not give definitions, but in this case, a typical trajectory covers all the phase space, all the whole energy levels densely, and moreover, we have some strong statistical properties of the dynamics. And this class is both these classes are in a sense very small classes. So this is nowhere dense, and this is open class in the world of all Hamiltonian systems, but still in applications we see this very rarely. And almost all systems we deal with is somewhere in between. And what we have in between, just few words. Suppose we are in near integrable situation. Near integrable. And in this system, in this class, more or less, we have the following. According to the KAM theory, many invariant manifolds, many invariant tori still survive. I mean, for example, positive topological entropy, and in fact we will see later that topological entropy is not very good way to measure chaos, but still this is what we can prove, and in fact it would be better to measure chaotic properties by some other quantities like measure entropy, but unfortunately the corresponding technique doesn't exist now, and even in some simple cases it is very hard to prove positiveness of measure entropy. So, but still the picture is as follows. So some integrability on a counter set of positive measure, and chaos in between. I say here near integrable situation, but even in a generic system, which is not close to an integrable, we can find in general some elliptic periodic orbit, and in many cases it is possible to do, and near an elliptic periodic orbit we have locally this situation, near integrable situation, and so locally in some small neighborhood of an elliptic periodic orbit, the situation is like that, is near integrable. So we can say that this picture occurs more or less generically. And so, but in my talk, I will show you a collection of examples where both integrability and chaos occupy sets, open sets. I don't want to say that that these examples are extremely meaningful, because all of them are a kind of exotic examples, and but still I believe that it is sometimes it is important to keep in mind these examples to avoid some naive conjectures and so on. So I start with the simplest example. This is pendulum, two pendulums. So we have two ordinary pendulums, and suppose that that this distance is a, and they do not interact. Suppose that they do not interact until they collide. And in this case, this means that if the amplitude of their oscillation is very small, then we have separation. The system is separated into two independent systems with 1 degree of freedom, and so we have obvious integrability. But as soon as they start to interact, as soon as they start to collide, when the energy is large enough, then certainly the collision, we can suppose to have Hamiltonian system. We should suppose in some set where the distance between them is smaller than some epsilon, which is less than a. So to have a possibility for them to oscillate without interaction, and if the potential of interaction is supported on this set, then certainly we have open set interface space where we have integrability, and an open set where we have interaction, and we don't have any reasons to suppose that integrability survives. So the second example is some geodesic flow which was proposed by Bolsonov and Taiman. The manifold is as follows. So first consider a direct product of two torus and real line. And here we have coordinates x and y, and here z. And we have the map x, y, z is mapped to some matrix. I will write down it in a minute, and z plus 1. So on this we have some map of this kind where A is the matrix 2, 1, 1, 1, the well-known Anosov matrix. And this map generates that action on this cylinder, and we can so this corresponds to 1, and we can take a quotient of this manifold T2 R with respect to this that action, and this will be our manifold. This will be M. And I want to define a geodesic flow. So I need a metric. I need a metric on this manifold, and the metric will be as follows. This will be dz squared plus some coefficients g11 dx squared 2g12. All these coefficients depend only on z. Dx dy plus g22 of z dy squared. And the metric will be these coefficients will be as follows: gy1, gy2, gy2, g22. This will be exponent of minus z g0 transpose, but in fact, this matrix will be symmetric, so transposition is not is not important. And so this will be this symmetric matrix, and G0 is calculated from this equation. So this is a logarithm of A. And so this is well defined analytic matrix on this manifold. And now what about geodesic flow? In fact, it is integrable. Why? So on the covering space, on this space, so on T2 times R, on this space we have three first integrals, commuting for first integrals. The first one is energy. So I do not write down Lagrangian, Hamiltonian here, it is standard in this situation. The second one is, we see that the matrix doesn't depend on y and on x. And so the corresponding momenta, px and py, are first integrals. And but unfortunately, only this function is a function on M. These two functions are multivalued on the manifold M. So to have first integrals on this manifold, we should try to consider some single-valued combination of these integrals. One combination is, I believe, this one, px squared minus px py minus py squared. So it is possible to check that this is a single-valued combination of this integral. So again, integral. So it is well defined on M. And another combination is more complicated. I even do not write down a formula. And another combination is some smooth function of px and py. And now these three functions, h, this one and this one, again give us a complete set of integrals. So the system is integrable, but only smoothly integrable, with smooth set of integrals. And almost so any energy, non-zero energy level is foliated by tori, except some set of zero measure. But on this set of zero measure happens something strange, because we can consider some special invariant set on say energy 1 surface in the phase space. So the phase space here is cotangent bundle to M, and so N, which is invariant set, is as follows. It is p x equals p y equals 0 and pz equals 1. So geodesics which go exactly in the direction of this R. And on this set, the dynamics is you can imagine that the dynamics is very simple. So the cross section of this flow on n, cross section of the geodesic flow on n is just x, y is mapped to a, x, y. And this is one of the most chaotic maps which exist in the nature. So you have here everything Anosov property and so this set supports positive topologic entropy, and so we have chaos. This chaos lives on a set of zero measure, but still it coexists with complete integrability. So very strange example. And so this is example number 2, and there is some generalization of this in papers by in a recent preprint which I believe now exists in archive by Wojtkowski. So generalization. A big collection of generalizations of this idea, and I do not comment because the constructions here are at least partially similar to this one, but more complicated. And the fourth example. What is the fourth example? This is mushroom. Bunimovich mushroom. This is another strange example as follows. So this is billiards. Everybody, I believe, in this room knows that a billiard in billiard system inside an ellipse is integrable. So billiard means that the particle moves in the domain as a free particle, and collision with boundary is elastic. These two angles coincide. And when you have an ellipse, we have an integrability in and the geometric mechanism is as follows. So any trajectory, if it has a tangency with some confocal ellipse or confocal hyperbola, then if it has one tangency, then it is tangent forever. Any link of that billiard trajectory is tangent to the same confocal if we consider 1/2 of the ellipse, then it is again integrable. Then it is again integrable. So more or less everything, the mechanism is the same. And so here, and so on. And now Bunimovich proposes to remove this this part from between the two focuses. So we have a hole here, and we draw here some rectangle, a leg of the mushroom, and this rectangle should be big enough downstairs. And now what we have? We have the trajectories which were tangent to confocal ellipses. They do not feel this all this construction. They do not feel this leg. So the integrability preserves for trajectories which are tangent to ellipses. But trajectories which were tangent to confocal hyperbola, which go this in this domain. Now they have big space to go down, and because now in this situation some mechanism of defocusing, which was proposed by Bunimovich, produces hyperbolicity. So I do not want to comment this much, but because of this big space for trajectories to go down and to collide with this rectangular part, we have that Bunimovich mechanism of defocusing gives hyperbolicity for this part in this part of the phase space. And so in this situation we again have coexistence of integrability in the head of the mushroom and hyperbolicity here in the leg. And the next example is another billiard. So suppose that we have some local picture now at the moment, a local picture of the billiard curve, and even in this picture we have at least one trajectory which goes trajectory of period 2, which goes up and down. And the question is it possible to find this billiard curve? Suppose, for simplicity, suppose that this curve, the billiard curve, is symmetric in both x-axis and y-axis. And the question is it possible to find the billiard curve in such a way that the dynamics is linearizable? So in some coordinates, the billiard map starts to be linear, exactly linear in some neighborhood of this periodic orbit of period 2. This is some maybe some strange question, and when I asked this question, I knew that more or less I knew the answer. That I was sure that the formal answer to this question. I mean that if we try to find the expansion of this part of the billiard curve is you see that it is natural to regard it as a graph of some event function. And if we produce, so this is the graph of the function f, and if we produce some Taylor series for this function f at 0 plus f2 x squared plus and so on, then I understood that the more or less that generically the series exists, and more or less I understood that it should diverge. And the answer turned out to be the following: that if when I say that the dynamics is linearizable, then, for example, this means that the dynamics is conjugated to rotation, to some angle. So we have some parameter here, angle of rotation, and on some plane, rotation by alpha, such that the dynamics here is locally conjugated to this rotation, to the angle. And if this angle is divided by pi is irrational number, not depend to q, then the series exists. This is the theorem. Very simple, but the theorem. So after that I started to I chose some angle alpha. For example, we can take alpha divided by pi is golden mean, and we can compute this coefficients just by computer. And very strange thing happened. A computer shows convergence of the series. That was extremely unexpected for me. And the conjecture is now that the series converges. So the radius of convergence is not zero for this series. But still, I don't have any theorem on concerning this. But still, computer shows that the radius of convergence of this series is not small, and this function exists in some not very small domain, and even in this graph numerically is continued so that it goes upper than x-axis, and the symmetric part will be this one. And now we can remove these small pieces, this and this, and we consider this smooth piecewise analytic curve, this one, and consider a billiard, and so here and an open part in the phase space contains the dynamics which is conjugated to this rigid rotation. And so we again obtain an example of this kind, and I just mentioned that recently numerically one of my student computed which if this integrable part in the phase space, big or small, and he according to his computation, for some angles alpha, almost 1/2 of the phase space is covered by integrability, and so this means that quite big part can be integrable in this situation. And, another example, number 6, is again about a geodesic flow, but magnetic geodesic flow. So we can consider some surface of genus greater than 1, greater or equal to 2. So sphere with 2 or more handles. And we know that in this surface we can consider matrix of constant negative curvature. And everybody knows that the corresponding geodesic flow is hyperbolic, so extremely curved. But now consider, and moreover, we know that such a surface can be considered as a quotient of the Lobachevsky plane. This is upper semi-plane xy. With respect to some discrete group of isometries, but consider another ingredient in the system. We consider also a magnetic field in this situation, and I write down a Lagrangian in coordinates which are taken from this Lobachevsky plane. The Lagrangian is as follows: x dot y dot square 2y square, and this is exactly Lobachevsky matrix. And now magnetic field. So some coefficient a and times something linear in velocities. This one. And when we make some computations, we see that if the energy in this system is less than a square, then all trajectories are the magnetic field is dominant in this situation, and all trajectories are closed. And so all trajectories are closed, and so we have obvious integrability. And in the contrary, if energy is greater than a square, then the kinetic part is dominant, and then trajectories, all trajectories, at least here on the covering space, they go to absolute there, and this can be regarded as a perturbation of this part of this purely kinetic part, and we know that a small perturbation of a hyperbolic system is again a hyperbolic system, and so we have chaos here. So small energy implies integrability, and large energies imply chaos. And just few words about another the last example. There is a well-known book by Bessie, lectures about manifolds on which all geodesics are closed, and it is possible to so this is number what 7. So manifolds with don't know, all geodesics.
Она на русский переведена разве?
Переведена. Close. There is a Russian version of this, Russian translation of this book, and there are many examples in that book, but I mentioned here only some simplest examples. So suppose that we consider manifolds of rotation, so with rotational symmetry, and so like that. And it is possible to find metric in this case such that all geodesics will be closed. But it turns out that, and this is very classical, and it turns out that unfortunately, except the standard sphere, all this metric have some singularities, conic singularities there, and this means that if we do not want to have singularity, we can smoothen slightly the metric here, the manifold here, and again this smoothing, the price for this smoothing is a lack of integrability of maybe if the smoothing breaks the symmetry, then we have lack of integrability, and again we see. But in this case we have not even integrability, but super integrability, because all orbits are closed, and so a part of the phase space is integrable, and moreover super integrable, and on another part we have something else, and maybe chaos. And so this is all I wanted to tell you. Thank you for your attention. Thank you.
Are there any questions or remarks?
Maybe just a quick technical question about example 5. So you mentioned some illustration or some hints that computer simulation might suggest that the series may be convergent. So
Yes.
the question is that how many terms did you take into account, and are all those terms correspond to even power. So let's
So you see only even Taylor coefficients are non-zero, and so up to number 300, and in fact that computer evidence of convergence is not just that the coefficients grow, do not grow much and so on. The evidence is more convincing for me because it is possible to see some asymptotic behavior for these coefficients, and these coefficients satisfy very clear asymptotics, at least numerically. But I am not able to see this